Hello, everyone. I would like to uh, thank the organizers for giving me this opportunity to speak online remotely at the ninth International Conference on Astronomy and Relativistic Astrophysics. I'm going to talk about the possible consequences of the length discretization on the metric tensor and the geodesic equation. My name is Abdel Tawfik from Egypt. This work has been done in collaboration with my colleagues, Abdel Majid Diab, Sam Shinawi, and Iman Abul Dahab. As a kind of a short abstract on my talk, we start from the so-called generalized uncertainty principle, in which the gravitational impact are taken into account in the Heisenberg uncertainty principle, and accordingly we modify this Heisenberg proposal. This modification, this generalized uncertainty principle, suggests a kind of length discretization or quantization, if you like. Um, the, the aim of our research is to try to analyze and understand the impact of this generalization, which also modifies our understanding on the precision of uh, length and momentum, time and energy, and so on. We try to understand its impact on the Einstein field equation. In this talk, we focus on the metric tensors, line metric, and the geodesic equation. The main question, the main problem and questions. The main problem is the gravity quantizations. This is a long-standing problem in physics. First, it's very obvious that this requires spacetime quantization, if possible, or discretization at least. Or, in other words, is some fundamental limits on length and momentum, for instance, time and energy, and so on. If we recall the Einstein field equation, this one, we see that the left-hand side contains the geometry, curved geometry, space-time curved geometry, and the right-hand side contains other parameters such as the gravitational constant, speed of light, but also the energy momentum tensor. The energy momentum tensor is quantizable. It's very apparent that. While the geometry, the space, is not, at least yet. But over the last few years, we have various models based on string theory, based on Gedanken experiments, based on cosmological observations. They predict minimum measurable length, space discretization. Minimum measurable length together with maximum momentum would suggest a generalization to the Heisenberg uncertainty principle. In such a way, what we have is we start from the delta x delta p greater than h bar over 2 multiplied by 1. This is up to this part we are dealing with Heisenberg. But if we take into account the generalization, we add another correction, which is this one. This is just a beta, some GUP parameter, multiplied by the expectation value of the momentum operator squared. Or in other words, we can also expand this expression to h bar over 2 multiplied by 1 plus beta multiplied by delta p squared, the precision of momentum squared, the precision squared of beta of p plus p multiplied by the expectation value squared expectation value of the momentum p. The T mu nu in the Einstein field equation is quantizable, as we said. Then the main question is, would you suggest quantization for left-hand side of Einstein field equation, and how look like the metric tensor, the line metric, and the geodesic equation? We start with a very short comparison between quantum mechanics and general relativity. At least with respect to the interactions. The quantum mechanics explains interactions through exchange of particles. This theory is inherently probabilistic. For instance, we can write the Schrödinger equation in this form. While the general relativity describes that the gravitational interaction is a manifestation of the space-time geometry. As we said, this is a space-time geometry. This part is a space-time geometry, while this one is controlled by the energy momentum tensor, by the contents, by this part, T mu nu. In this field equation, G mu nu plays a central role, and the free particle move along geodesic, which can be described by this expression. Also, G mu nu governs this motion and emerges the effects of gravity, while the matter content in T mu nu affects the space-time curvature, and the entire Einstein field equation describes how the space-time geometry is governed, is dictated, is controlled by matter. Also, now we recall the GUP, one of its different proposals. The whole GUP proposals, or the entire ones, or the entire work was GUP based on an attempt to quantize the gravity. Quantum gravity predicts a quadratic or quadratic-momenta-corrections to the Heisenberg uncertainty principle. This at least was the motivation of Kempf-Mangano-Mann, who suggested that the commutation relation of xi and pi, length and momenta, equals IH bar multiplied by delta ij plus beta 0 multiplied by delta ijp squared divided by mbc all squared plus 2 beta 0 multiplied by pi bj divided by mbc squared again, where beta 0 is the GUP parameter, which can be or should be or is to be determined from cosmological observation and other Gedanken experiments and theoretical motivation. Accordingly, we can have the uncertainty principle delta xi multiplied by delta pi. This equals to h prime divided by 2 multiplied by 1 plus beta divided by mb. mb is the blank mass. C all squared multiplied by delta p squared plus expectation squared expectation value of p plus 2 delta pi squared, the precision of pi, plus 2 the squared expectation value of bi in this form, where pi and p squared and so on are explained. Accordingly, we have a minimum length, a minimum measurable length. This is the square root of 3 beta 0 multiplied by the Planck length, where Planck length is the square root of h bar, gravitational constant, divided by c cubed. Of course, this is not the only proposal for GUP. There are various ones. For instance, Maggiore proposed that the commutation relation xi pj equals ih par delta ij multiplied by the square root of 1 plus gamma 0 multiplied by mbc squared divided by mbc squared multiplied by b squared plus mc squared. This expression is motivated by quantum deformation of the Poincare algebras, another motivation. And accordingly, the minimum length reads delta x minimum equals to the square root of gamma 0 divided by 2, where gamma 0 is the GUP parameter, multiplied by LP, the Planck length. Now we start. We start our research. We start with non-commutation relation, inspired by GUP. The non-commutation relation of quantum operators can be expressed as, for instance, operator xi and operator pj. The commutation relation, we assume this greater than or equal to delta ij I h bar multiplied by 1 plus beta p squared. This for simplicity, where p squared equal gij p0i p0j, and jij is a Minkowski spacetime metric tensor, for instance, minus plus plus plus, and the operator is xi equals x dot I multiplied by 1 plus beta p squared, while the operator bj equals p0j. Of course, both operators x0i and p0j are similarly deduced from corresponding commutation relation, such as this one, xi0 p x0i and p0j equals delta I h prime. Such commutation relation can be included in spacetime geometry through enlarging the Minkowski manifold to an 8-dimensional spacetime, tangent bundle-like. XA, capital A here, where capital A runs from 0 to 7, equals to x mu of ZA and beta x dot mu of zeta A, where x dot mu equals to dx mu by ds. When doing this, we can now compare between the Minkowski line metric and the modified Minkowski line metric. The Minkowski line metric in this form, ds squared equals g mu nu dx nu, while the modified one, ds delta squared equals correspondingly, similarly, straightforwardly, GAB, capital B, dx capital A, dx capital P, where A and B runs from 0 to 7, while mu and lambda so far from 0 to 3. Also lambda, which appears later on, runs from 0 to 3. GAB, the metric, GAB equals G mu nu cross G mu nu. Just to remind you about the 8-dimensional manifold, this can be deduced to the 4-dimensional one. This is the 8-dimensional one. Accordingly, the modified 4-dimensional metric tensor is then given as G tilde mu nu equal GAB, given before, delta XA delta Z mu delta xp delta z nu. We'll do some algebra. We come up to this expression where we have here g delta mu nu equals to 1 multiplied by g mu nu. This is the standard expression of general relativity, and this is a correction term. This term reads beta x double dot lambda x double dot lambda, where x double dot is just the derivative of x dot mu, for instance, or lambda. For a flat space, we assume, or where g mu nu equals to eta mu nu, then the modified metric tensor can be written in this form: g delta mu nu, the modified one, equals 1 plus beta x double dot lambda all multiplied by eta mu nu, where this can be simplified as eta mu nu plus h mu nu. This h mu nu is a correction added to the metric tensor here, where the h mu nu, which equals beta x double dot lambda eta mu nu, expresses the quantum correction due to GUP. Of course, it's obviously if h mu nu goes to 0, then the GUP contribution diminishes, and the Einstein field equation are restored straightforwardly. This means that the principle of general covariance is satisfied even in absence of gravitational effect on the modified Minkowski metric. Doing this, we can now write down an expression for the modified 4D line metric, which reads ds delta square is equals to 1 multiplied by ds square. This is the general relativity one. But we obtain the correction one, which is beta squared x double dot lambda x double dot lambda. This expression, this term, counts for the quantum correction due to GUP. Now, we come to the modified geodesic equation. We use a variational principle, and we extremize the path SAP. Then the special relativity and general relativity could be generalized, so modifying geodesic equation. We can distinguish between flat space and curved space. For flat space, geodesic reads beta L d square by d tau square of h dot mu minus d dt of x mu plus some correction equals to 0, where beta is includes the GUP parameter, L is a Lagrangian. For the curved space, we have a very complicated expression. This reads something like this, where for simplicity, or at least, or from the first glance, you can justify that if beta, the parameter, the GUP parameter, goes to 0, I mean the GUP effect diminish, then we obtain the standard GUP geodesic equation. This one. All expressions here are explained. For instance, this tau and x dot mu explained before, g mu nu comma alpha, g mu alpha comma gamma comma beta, and this gamma squared mu nu, or even the Lagrangian, are expressed in this way. The results we have obtained means that not only acceleration of a test particle in the gravitational fields is included, but also our geodesic equation includes higher derivative as well, namely snap means the fourth order derivative of the line element, and the snap is also is obviously derived from the jerk, the third order derivative. But just to remind you, the acceleration, as in Einstein geodesic equation, without jerk is just static load, i.e. neither vibration nor transition is allowed. Jerk gives the change in the force acting on that test particle, while snap is resulted from the change in the jerk itself. Both quantities in our results are finite. This means some vibrations occurs, especially for multi-resonant mode or for a sudden transition between different radii of the curvature. This allows us to try to implement our results on observation, especially the most recent ones, that the expansion of the universe is accelerated. This could be understood based on various proposals, like I modified J and so on, f of J, f or and so on. But our study or research suggests that GUP could play a role in explaining the accelerated expansion of the universe. It means, accordingly, the geodesic equation, the path, the motion of this particle in the universe is not only described by the acceleration itself, but the higher derivative of the acceleration, change of the acceleration. Yeah. We need more study to crystallize, to draw concrete conclusion about this one, but we think that our results, which is in the first stage right now, is a promising one. As a summary, what we have done is we started with GUP, we started with modified commutation relation between x and p, length and momentum, which is based on this p parameter. Accordingly, we have obtained a line metric, modified one, which contains a correction term, this one. And we also obtained the line metric, which also again is corrected with this term, beta squared x double dot lambda x double dot lambda ds squared. And for the geodesic equation, we have two expressions, one for the flat universe, for flat space, and one for the curved space. As I said, for the curved space, we have various corrections which come up or include higher derivative of the acceleration of the line element. Thank you very much for your attention. Thank you.